In this video, we will cover how to predict whether the reactants or the products will be favored in acid-base reactions. Remember that in every acid-base reaction, there will always be one acid and one base on each side of the equilibrium arrows. Every acid-base reaction is made up of two conjugate acid-base pairs. Because the conjugate base of a strong acid is weak, and the conjugate acid of a strong base is weak, the weaker acid and the weaker base will always be found on the same side of the equilibrium arrows. Furthermore, the formation of the weaker acid and the weaker base is favored. Another way to think about this is that the stronger acid and the stronger base both want to act like a strong acid and a strong base. Therefore, they will react and push the equilibrium away from themselves towards the products, which are the weaker acid and the weaker base. If we have the Ka and Kb values, or pK and pKb values, of the acids and bases involved in the equilibrium, we can use these values to predict whether the reactants or the products are favored. Remember that a higher Ka or Kb value, or a lower pK or pKb value, indicates the stronger acid or stronger base. If we're given the acid constants, we want to compare the two acids in the reaction. If we're given the base constants, we want to compare the two bases. So, for example, if we're given a pKa table, we will want to compare the strengths of the two acids, one on each side of the equilibrium arrow. Whichever acid has the lower pKa value will be the stronger acid, and whichever has the higher pKa value will be the weaker acid. The side of the reaction that contains the weaker acid will be the favored side. If we don't have pK or pKb values for the acids and bases involved in our reaction, we can instead predict the strength of the acid or the strength of the bases based on their structures. Remember that talking about the strength of an acid or a base is just another way to talk about the stability of that acid or base, or in other words, the energy of the acid or the base. A weaker base is a more stable or lower energy base. A weaker acid is more stable and lower in energy. In other words, acid-base reactions favor the formation of the weaker and more stable acid and base. Therefore, in order to determine whether the reactants or the products are favored, we need to either compare the acids on both sides of the equilibrium arrows or the bases. We can compare the relative strengths of both acids or both bases. When comparing acid or base strength based on structure, it's often easier to compare the bases. Next, we will discuss the structural factors that affect the relative stabilities of acids and bases. The first factor that we will consider is the electronegativity of the atom bearing the charge. An electronegative atom will be happier with a negative charge. An electropositive atom will be happier with a positive charge. By happier, I mean more stable, indicating the weaker acid or the weaker base. For example, if we compare bases where the negative charge resides on carbon, nitrogen, oxygen, or fluorine, which are all in the same row of the periodic table, remember that electronegativity increases as we go from left to right. Carbon is the least electronegative, followed by nitrogen, then oxygen, then fluorine. If we consider anions where the negative charge resides on each of these atoms, stabilities will increase in the order of electronegativity. In other words, the carbon bearing the negative charge is the least stable anion, followed by when nitrogen has a negative charge, then oxygen, then fluorine, which is the most stable because it's the most electronegative. The basicity of these different bases then follows the opposite trend. The least stable anion, CH3-, will be the strongest base, followed by NH2-, then OH-, and finally F-, which is the most stable anion and therefore the weakest base. Remember that the acidity of the conjugate acids of these bases is inversely related to the strength of the bases. Therefore, we will see the reverse trend for the conjugate acids of these bases. Because CH3- is the strongest base, its conjugate acid will be the weakest acid, followed by ammonia, water, and finally hydrofluoric acid, which is the strongest acid of these four. The second factor we will consider is the size of the atom bearing the charge. A larger atom can allow the charge to be spread over a larger area, making the ion more stable. In other words, this ion will be a weaker acid or weaker base. Remember that size increases as we go left and down along the periodic table. For this example, we will compare the halides. The size of the halides increases as we go down the periodic table. Therefore, fluoride is the smallest ion, followed by chloride, bromide, and iodide. The smallest atom will make the least stable anion, and the largest atom will make the most stable anion. Therefore, fluoride is the least stable ion, followed by chloride, bromide, and then iodide. The trend in basicity will be reversed. Fluoride is the least stable ion, and therefore it is the strongest base, followed by chloride, bromide, then iodide. The acidity of the conjugate acids will show the reverse trend. The strongest base, fluoride, will have the weakest conjugate acid, hydrogen fluoride, followed by hydrogen chloride, hydrogen bromide, and then hydrogen iodide. Notice that the trend in basicity is exactly opposite of what we would predict if this were based on electronegativity. Fluoride is the most electronegative of these atoms, but it is still the strongest base. That's because when we go up and down within a column on the periodic table, size changes much more rapidly than electronegativity. However, when we go left and right, electronegativity changes more rapidly than size, and so that's the deciding factor when comparing atoms within the same row. The next factor we will consider is the resonance stabilization of an ion. When comparing bases or acids, if one of the bases or one of the acids is resonance stabilized, it will be more stable and therefore a weaker acid or a weaker base. Resonance increases stabilization and decreases acidity or basicity because it helps to delocalize the charge. It spreads it out over more than one atom. Let's look at an example. If we compare the relative basicities of a ethoxide ion and acetate ion, we can see in both cases that the negative charge is located on an oxygen atom. Therefore, there is no difference in electronegativity or size between the atom bearing the charge in both of these bases. The difference in basicity here lies with the fact that the ion on the right can be resonance stabilized, where the one on the left cannot. Resonance stabilization in this case helps to delocalize the negative charge over the two oxygen atoms, giving each one a half negative charge, and therefore stabilizing this ion relative to the ethoxide ion. Because the acetate ion is more stable, it is therefore a weaker base. Remember that this also means that it will have a stronger conjugate acid. The fourth and final factor we will consider is called the inductive effect. While resonance involves the movement of full charges to different atoms within the ion or molecule, you can think of the inductive effect as kind of like moving partial charges throughout the molecule. It functions in the same way, though, in that it leads to stabilization of the ion, leading to a weaker acid or a weaker base. We see the inductive effect when there are electron withdrawing groups close to the negatively charged atom of the base, or electron donating groups near the positively charged atom of the acid. These groups polarize the electron density through covalent bonds, helping to stabilize the charge. Let's look at an example. These two bases differ only in the replacement of a hydrogen in the base on the left with a chlorine atom in the base on the right. The addition of the chlorine atom helps to withdraw electron density away from the negatively charged oxygen through the covalent bonds within the ion. This stabilizes the negative charge of the base on the right, making the base on the right the weaker of the two. The magnitude of the inductive effect changes with both the electronegativity of the atom as well as the distance of that atom from the charge that it's helping to stabilize. Let's look at two more examples. If we compare the strengths of these two bases, the one on the left is stronger than the one on the right. Chlorine is more electronegative than chlorine, so it pulls harder on the electron density in that ion, helping to stabilize it more than the chlorine can stabilize its ion. Additionally, if we compare these two bases, the chlorine has a larger effect when it's closer to the negatively charged atom that it's stabilizing. Therefore, the ion on the right is more stable and is therefore a weaker base. Now let's briefly review the factors that affect the strength of acids and bases. First, the electronegativity of the atom bearing the charge. Second, the size of the atom bearing the charge. Third, any resonance stabilization available to the ion. And finally, the inductive effect. When deciding which of these factors is at play in determining the relative strength of a set of acids or bases, you need to consider first whether the charge is on different atoms or the same atom in each of your acids or bases. If the atoms are different, then it's probably electronegativity or the size of the atom that's affecting the strength of the acid or base. If the atoms bearing the charge are different and are in the same row of the periodic table, it's electronegativity that will make the decision in which is the strongest acid or base. If the atoms bearing the charge are in the same column, it will be size that is the determining factor. If the atoms bearing the charge in both acids or bases are the same, then you need to look to rules 3 and 4, resonance stabilization or the inductive effect, to determine the difference in strength.